Did you ever wondered what are solar power plants and how do they work? If you did, then you came to the right place. Hopefully this video will answer all of your questions, so let's dive right in. A solar power plant utilizes the energy of the sun to produce electricity. The key processes are as follows: photon absorption, photovoltaic effect, creating current conversion from DC to AC distribution, and energy storage. These are the basic stages that describe how a solar power plant produces electricity. What is photon absorption, you may ask? Photon absorption is the process by which an atom, molecule, or semiconductor absorbs a photon, a particle of light, and thereby gains its energy. Here's a deeper look into how it works. Photon interaction with matter. When a photon, traveling as a wave packet of light, encounters an atom or molecule, it interacts with the electrons orbiting the atomic nucleus. The energy of the photon is transferred to one of these electrons. Energy transfer. If the energy of the photon matches the energy needed for an electron to move to a higher energy state, also known as an excited state, the photon is absorbed, and its energy is transferred to the electron, resulting excitation. As a result, the electron moves to a higher energy level, away from the nucleus. This leaves a vacancy or hole at the lower energy level where the electron initially was. Over time, the electron will usually drop back down to the lower energy level, releasing its gained energy in the process. In the context of solar panels, the absorbed photon provides enough energy for the electron to overcome the band gap of the semiconductor material, typically silicon in solar panels. The electron moves into the conduction band and becomes free to move through the material. This movement of electrons is what we call electric current. Now, when we know what photon absorption is and how it works, let's explain the photovoltaic effect. The photovoltaic effect is a process that converts light, photons, into electricity, voltage, at the atomic level. It was first observed by French physicist Edmond Becquerel in 1839, but the underlying principles were not understood until Albert Einstein provided a theoretical explanation in 1905. Here's a breakdown of how it works. Absorption of light. When sunlight strikes the surface of a photovoltaic or solar cell, usually made of a semiconductor material like silicon, photons from the sunlight are absorbed by the material. Creation of electron-hole pairs. The energy of the absorbed photons is transferred to electrons in the atoms of the solar cell. If the energy given to the electron is sufficient, it can break free from its atom and move around freely. This action leaves behind a hole. The process of creating these free electrons and holes is known as excitation, movement of electrons and holes. The photovoltaic cell is built in such a way that it creates an electric field across the semiconductor. This field causes the electrons to move towards one side, the N-type side, and the holes towards the other side, the P-type side. Creation of electric current. If an external electrical circuit is attached to the cell, the movement of these electrons can be harnessed, and an electric current is created. The electric field within the cell provides the voltage. The photovoltaic effect is the basic physical process through which a solar cell converts sunlight into electricity. Sunlight is composed of photons, or particles of solar energy. These photons contain various amounts of energy corresponding to the different wavelengths of the solar spectrum. When photons strike a photovoltaic cell, they may be reflected, pass right through, or be absorbed. Only the absorbed photons generate electricity. Well, that was interesting. But what about creating current? How does the solar power plant do that? Creating an electric current involves the movement of charged particles, typically electrons, through a conductor, like a wire. Here's how it works in the context of a photovoltaic cell, like in a solar panel. Absorption and excitation. When sunlight, composed of photons, hits the photovoltaic cell, photons are absorbed by the cell's semiconductor material, typically silicon. The energy of the absorbed photon is transferred to an electron, allowing it to break free from its atom. This process creates an excited electron and leaves behind a hole. Creation of electron-hole pairs. The excited electron, negative charge, and the corresponding hole, positive charge, form an electron-hole pair. This process of electron excitation creates a difference in electric potential within the material. Movement of charges. An electric field is established within the cell due to the cell's p-n junction. created by doping the semiconductor material to create a side with an excess of electrons, N-type, and a side with a deficiency of electrons, P-type. This electric field pushes electrons to one side of the cell and holes to the other side. Establishing an external circuit. When the photovoltaic cell is connected to an external electrical circuit, like a wire connecting to a light bulb or an electrical grid, the electrons are able to travel from the side with excess electrons through the external circuit and towards the side with a deficiency of electrons, creating current. As these electrons move through the external circuit, they create an electric current. This current can be harnessed to power electrical devices. Recombination. Once the electrons reach the other side of the cell, the side with a deficiency of electrons, they fill the holes where electrons were initially excited. This recombination process allows the cycle to begin again when new photons are absorbed. It's important to note that in a direct current, DC system, such as a photovoltaic cell, the electrons always flow in the same direction. In an alternating current, AC system, used by most power grids and household outlets, the direction of electron flow alternates. The conversion of direct current, DC, to alternating current, AC, is done by a device called an inverter. This process is crucial in systems like solar power generation, where the electricity produced is in DC form, but needs to be converted to AC for use in most home and industrial applications, which run on AC power. Here is a basic explanation of how the process works. Direct current, DC. DC is an electric charge that flows in one constant direction. It is the type of current produced by photovoltaic cells, solar panels, and batteries. The issue with DC is that it is not easily converted to different voltages, and it loses efficiency when traveled over long distances, which makes it less suitable for most home and industrial uses. Alternating current, AC, AC, on the other hand, is an electric charge that periodically reverses direction. The voltage in AC can be easily changed by transformers, making it more suitable for transmission over long distances and use in different types of applications, from charging a phone to powering an industrial machine. The role of an inverter. The inverter's job is to take the DC power generated by the solar panels and convert it into AC power. It does this through a complex process of electrical engineering, including switching and electronic control to produce AC current waves from the DC source. There are different types of inverters, including square wave, modified sine wave, and pure sine wave, each providing different quality of AC power. Modern inverters also manage the system to ensure that the solar panels operate at their maximum power point, where they generate the most power, and protect the system from issues like overvoltage or grid failures. Once the DC power is converted into AC power by the inverter, it can then be used to power your home, fed into the grid, or stored in an AC battery system for later use. Distribution and energy storage are key aspects of a solar power system. Let's break down both. Distribution of solar power. Once the solar power is converted into alternating current, AC, by the inverter, it can be distributed for use. The power is typically sent to an electrical panel, often called a breaker box, which then distributes the electricity throughout a building using electrical wiring. The electricity can power lights, appliances, electronics, and other devices. For larger-scale solar installations, like a solar farm, the electricity produced is sent to a substation where the voltage is increased for long-distance transmission on the power grid. The electricity is then distributed to homes, businesses, and other users through the power grid. Energy storage. Not all of the electricity produced by a solar power system is used right away. Excess electricity can be stored for later use. This is typically done using a battery storage system. These systems can store excess solar energy produced during the day for use at night, or during periods of low solar production. A battery storage system includes a charge controller to manage the flow of electricity into the battery itself, an inverter to convert the stored DC power back into AC power when it's needed, and a variety of safety equipment to protect the other components. Energy storage and efficient distribution are essential for maximizing the effectiveness and reliability of solar power systems. They ensure that the solar power produced can be used as needed, whether immediately or at a later time. Well, this was everything for today's video. Please consider subscribing, leaving a like and commenting on the video since it helps the channel grow. Thank you for watching and see you next time.